Okay, good morning, everybody. By Netster's weekly agenda. As usual, we have invited guests to share their experiences, to inform, communicate, and educate the market. One of the guests that we have again is our colleague, Graham Bolton. Graham, welcome on board. Thank you for coming. I have
Thank you,
Peter
Edwin.
here
Nice to be here.
from Netherlands, also as our managing director, and Maddie from Bucharest office. Maddie will be doing the broadcasting. Peter will be the host asking questions. And I'll have basically a brief introduction. Graham has been our repeated guest in our second session. We had a very good turnout on his subject, and people asked us to provide additional content and so forth. So we are delighted to have Graham as our guest. He's our, according to media, he's been labeled as our software detective. He's done various activities, which we have previously explained, with track records since 1982, bringing up to 7 billion raised through his efforts with his team in his database and so forth. So without further ado, we want to talk about the 5 resource bottlenecks in big data. So Graham, take over.
Thanks, Ahmed. As you say, I'm going to be talking about bottlenecks in big data. It's actually bottlenecks in processing. It applies to practically everything. 20 years ago, this was very important for everybody. Now it's only really important when you're dealing with a lot of data. So I'll kick straight off. One of the issues is the 5th resource is very difficult to deal with. And I'll come to that at the end. First, I have to explain the first 4. So if you look at the topography of a typical system, these days, sitting at home with our browser, connected to our PC, and we want to get some data. So if we want to get access to data, we typically won't go straight to a disk. We'll go via something like a DBMS. And often times these days, of course, we'll be using an application in between the user and the database, because we don't want the users to have all the access they could have through a database. We want to restrict them to certain access paths, certain secure arrangements for looking at data. So this is your typical topography. So the user has to contact the application, which has to contact the database management system, which then does access on the data, which is then returned from the DBMS to the application and then out to the user to be shown. So this is the topography of most systems these days. And of course, they can be more complicated. There can be different application servers working together. You could be accessing multiple databases. It can get quite difficult. If we look at the resources involved, the bottlenecks, one of them is CPU power. Now, if we look at CPU in this particular picture, you'll see we start out with the CPU of the user. So that could be a very old computer or a very small computer with a slow chip. It could be one of the newest of the new with 4 chips, 4 CPUs on a chip, 8 CPUs on a chip, all good stuff. And it could just be your mobile phone, because that's also, of course, a computer. So that's CPU. We have no control over that. That is just a given. That's what the user has. Where we have some control is how much CPU power we've got at the back end. So if you like, at the application server and at DBMS. Now, you can add CPU power to these things, but really the CPUs these days, they'll do at least 1,000 million operations per second. Just remember that. That's quite a lot. So typically you'll have a few application servers and they'll have multiple CPUs on a chip. So you're looking at maybe if you've got 8 CPUs, you're looking at 8,000 million instructions per second. So if we're running short at that end, we're probably doing something wrong, frankly. Move on now to adding CPU. You can add CPU to your backend or to your database server quite easily by doing things in parallel. DBMS systems over here, they're designed to run with multi-threading. They've been running that way for 20, 30, 40 years. So it'll be a back-end process which can service multiple users at the same time. And also these days, applications programmers are having to write multi-threaded systems so they can take advantage of the multi-CPU systems which are available in the marketplace. So CPU power, if your programs are multi-threaded, it's a question of adding some more CPUs. But if you move to memory now, it's the same sort of thing. There's a local amount of memory that someone has in their computer. You don't have much control over that. Some people have a lot of memory, some people don't. And if you've written some inefficient stuff, which is running in JavaScript perhaps on the CPU, which is using memory, you may end up causing the system to page or to swap, which will slow things down considerably. But you don't have much control over that. And basically, the less you write here in JavaScript, the better. But if we move on to the application server, this is of fundamental importance. Now, one of the reasons we use memory is to cache data. If we get data from a database system and we cache it, we hold a copy for a while, it's much, much faster than having to go off the database and get the data. So you'll find if you cache things in the memory of your application server, it's very fast, but the disadvantage is the information is becoming out of date. So you could be showing information which is no longer valid. And the other thing is, if the user's changing data, you're going to have to maintain a consistent picture using something like a model view controller model to make sure that each question that the user asks is answered in a consistent way. But by far the best place to place memory in this topography of systems is on your DBMS server, because the DBMS server is designed to manage a cache store of data in its own memory, multi-user, the whole thing. So it's designed for exactly this work. And this, as I say, has been the same way for 20, 30 years. So this technology is fairly refined, it's fairly stable, and you don't have to replicate it yourself in memory, in the application server. So if you're choosing where you're going to put memory, add it to your DBMS server. And if you've got if you've got same configuration for applications and for database servers, you're doing the wrong thing. You need to have a different configuration for database machines because they have different resource use. So that's a discussion of memory. It's a way of avoiding going off to the disk. Now let's look at messaging. This is when the cost becomes clear of sending a message to and from or between the user and the application server. Well, there you're dependent on the big world of internet. You could be on a mobile line which has a latency. So you send a message and then sometime later the message arrives. And then you've got the transfer speeds. So those are interesting on the internet, very variable depending upon the connection that people have got to the internet backbone. And then you're dependent on this rather unreliable connection. So basically, the fewer messages you send, the better, and the smaller the messages are, the better. But if you want to send a lot of data, you'd rather have a few messages which are large than lots of little tiny messages one after the other. So as few messages, a few transmissions as you can, and as little data as you can possibly transfer, that means you're making good use of the facilities. Now, when you get to the data transfer between the application server and the database management system, basically you want to have them really physically close to each other because of E equals mc squared and the speed of light and stuff. You don't want there to be a huge distance between these two. So if you can co-locate these, that's better than having them spread around the globe, because your customer may be around the globe, but this is more intensive. This line between the application server and the DBMS is going to be more intensive than the line between the user and the application if you're doing your work right. So much for inter-process communications. But if we now move on to input-output, actually, this has been the core of practically everything for a very long time, because these operations here, you can do 10 to 100 operations per second. Now let that sink in, okay? We have a 2 gigahertz processor, which is doing at least 1,000 million things every second. And over here, we've got a device. It's a disk. So I should have got a disk. I'll use a dinner plate. We have a disk, and the head moves like this over the disk. And if it has to move from this edge right the way through to the middle, that will take 100 milliseconds. So it can do that 10 times a second. If it's moving from track to track to track, it can do that quite quickly. It can do that in 10 milliseconds, so it can do that 100 times a second. So disks, other than solid state disks, have physical moving parts. And what they do to make the disk work faster is they have little caches inside the disk, then they cache the information in DBMS to make sure we don't have to go off and grab information from the disk. However, if you have, with big data, very large data sets, you simply cannot cache everything. So the trick is to access things sequentially so that the information you're reading from the disk is coming from adjacent blocks. So if you organize your data on the disk in an efficient way, you'll hear this sound when you put your ear against the cabinet. It'll go tick, 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 tick. And if you haven't organized your data on the disk in an efficient way, you'll hear as the disk is moving to and fro. So there's a lot about computing that people don't understand because they've moved away from the computer. We've got more abstractions. We don't think about this stuff anymore. That's somebody else's problem. Oh, we can just buy more hardware. There's lots of fake solutions to these problems. But the thing is, with big data, you really are going to have to design where on the disk your data is put. And if you've got multiple machines, which is very likely if you're in big data, then you want to know on which machine it's being managed. And when you want to merge these things together, you're going to collect things locally without transferring it to an application. So you're going to be writing stuff that runs on a database server. So this is the fun. This still matters. The good old-fashioned disk with its one operation per 10 milliseconds, so 10 operations a second, 100 operations a second. This is what really matters. And it used to matter a lot for all applications, even simple business database systems. They would run slowly if you became disk bound, because all of the other things are cheap, all of the other things are fast, but disks are not. Now, solid state disks have helped, but they're still a lot slower than regular memory. So you really have to think about how to organize your information, even on solid state disks. So I also forgot to tell you that we have to deal with read-write. Yeah, so I was reading the information before. If you write to a system, there's an element of serialization occurring here. You have to write things away in the right order so that when you read them back, it's consistent. When you're reading, you can just grab. You can just read from a cache, and if you have multiple systems with mirrors, it can just accept the first copy you receive. But if you're writing to a database, there's some element of serialization where your transactions have to be stored, so they will eventually be written to disk in a secure way. So reading is 10 to 100 times faster than writing. So if you're writing a lot of information into in a big data situation, things get much worse, much quicker. So this is the broad story. The other aspect is, of course, the location of which disk you're putting things in.
Graham, does this also include uploading files when customers take big video packets of video and upload it? Does that have the same kind of an impact into the disk?
Well, in that situation, you're typically using your database to decide what physical disk to locate something on. So you'll have, rather than a database which contains videos, typically you'll have a database which contains the names of the videos, the lengths of the tracks, etc., and their physical location. So you're going to have to do some management of the disks yourself in order to store the information so that it can be pulled back from the server. But the point is, with videos, then you're looking at a write once, read many times situation. So a video is typically written to the disk once, stored, and it's just accessed by people. So you can have multiple copies stored on different locations to reduce access times. But broadly speaking, write once, read many times.
Understood. Thank you. Go ahead.
So if we look at this overall picture, we're looking at resources. So you can buy CPU, you can buy memory, you can buy disks, but what it comes down to is you still have to understand what you're doing, because of the intangible fifth resource, which is locking. So what is locking? Well, locking is basically resource contention. It means that you want to access the CPU when somebody else is using it. You want to access a piece of memory when somebody else is using that. You want to get a message sent, but somebody else got there first. You want to use the disk, but somebody else got there first. So the other aspect is database locking. It's very important to have a consistent picture when you read from a database. So you read a fact and you read other facts which are related as part of a transaction. Then at the end, those facts have to have been consistent. So if you've read with situation A and then you've read something else with situation B, then you've got two different pictures of reality. So with transactions, you actually have to stop other people from changing the database while you're reading it, or you have to read it from a copy. And both of these have costs. So with locking, it can be as bad as some paging and swapping going on the user's PC. So even though the user said go, there's something else happening on the PC where it's run out of memory, so it's having to copy something from the disk into memory or copy something from memory onto the disk so that it retains its state before it can actually send a message. Then, of course, we have this business of sending messages over the internet. So we have latency, which is where we send a message and it takes some milliseconds or perhaps a little bit longer to arrive at the place we were sending it to. And then it takes some time to transfer the data, because it's not just a small message, it's a big message. You've got transfer time. That depends on every aspect of the connection between the user's PC and your application server. Then we have the application server itself. There can be all sorts of things happening there. You've got a limited number of threads, for example, that you can't have any more threads than there are actually CPUs in some situations. So you don't have enough resource of either CPU or memory or disk on the application server. And then we have the inter-process communication between the application server and the database servers. And then we have the database servers themselves. And then we have the disks transferring information to and from the disks. And we also have that a particular spindle in the pack of disks could have all the data on it, which means that there's too much traffic on that particular spindle. So if we don't understand this, 20 years ago, 30 years ago, if you didn't understand this, you could write an application, design a database design, and it would perform well. And after a while, it gets too slow and you have to rewrite your program or reorganize the information. That's why we have relational databases, so we can index stuff later. This has sort of gone away because everything's much faster than it was then. So programmers have not had to learn about indexing. They've not had to learn about transfer times. They've not had to learn about a whole bunch of stuff to do with caching or how database management systems work. And now we're moving into the field of big data collectively. All of these things, basically, they amplify, the big data amplifies all these problems, amplifies the need to understand this set of circumstances which have been around probably 40 years, but have become irrelevant to most of the IT business. But they are still relevant in big data. You have to understand at the lowest level what's going to happen when you ask for data from a big data lake, if you like. So any questions at this point, guys?
Well, yes, I have some question on indexing. As you know, a lot of times indexing takes a lot of time, especially when the big data comes to formation and so forth. And we all been managing databases in the past throughout our career, so we understand the complexity and some of the time consumption that it requires. What is your feedback about the consumers? Because a lot of times, you know, let's say their system crashes or they run out of memory at the user level, and all of a sudden a record lockout takes place in the memory of a system, whether it's from one point to the other point. And then that client, for example, cannot get into that system because of that record lockout and so forth. What do you recommend in terms of remedies, or how do you perceive that can be resolved from the back-end side?
Well, there's a lot of way in which people deal with this business of locking, because locking is the intangible resource. If it's done for you automatically by the DBMS, then there's a whole bunch of things which aren't going automatically. So, for example, there you are, Ahmed and Peter. If Peter reads a record from a database and Ahmed reads the record, and then Peter makes one change and Ahmed makes another one, whoever wrote last writes over the change made by the other. So that's called a lost update. So we have to protect users against this. So for example, we could say that you've both read version 1, and then when Peter writes back, he says, I'm writing back over version 1, and then the version number becomes 2. When Ahmed comes to do that, then he's trying to write back over version 1, and the system says, well, sorry, version 2 is there now. You can't write version 1 over version 2. You have to do your transaction again. So there's ways of doing this, but they have to be programmed, and they have a cost in this picture. You know, they've got a storage cost. You have to store the version number. They have a cost in terms of the DBMS of doing extra queries to say, hey, can I write over the data? So that's an extra query, and that has to be written in the program here. So you've got more messages going to and fro. So avoiding the problem of locking or making your own solution to locking is costly. Right. It's happening here. It's happening in this axis. So the user doesn't notice. They just do the normal thing. But down here on this axis, we've got more resources being used trying to avoid the locking problem. Does that answer your question, Ahmed?
Partially. And one of the challenges is, do you approach an example that you just mentioned between Peter, Ahmad, and we are, let's say, at the same time, access to the same record, right? And do you recommend LIFO, last in, first out, the FIFO, the first one who accesses the record gets the lock privileges? How do you recommend that?
Well, my recommendation is actually you put a lock on the record itself.
Okay.
So that means we have like normal screens for viewing information, but as soon as you say I'm going to change this, you take a lock with the intention of reading to update.
Got it.
So that involves either using a DBMS measure to do that. There are measures built into particularly SQL systems for doing a read for write.
Right.
But if you have to simulate it, you end up with a little extra flag saying Peter's got the record.
Right. Just like, for example, right now, let's say if you're using a Word file or an Excel file, we can do read-only. Or if you have opened it up in the memory, and then we can obviously release it, and then it gives us back the read-write privileges, right?
Yes. But the problem will come when Peter takes a lock on the data and then walks away, has a cup of coffee, and then goes home. Nobody else can access the record, so you have to have logic to control that, which means that...
Then we use a messaging system to say, come back and unlock, right? No, I'm kidding.
Mobile phones, we can call them up, but no. You've seen these things with Office products. You can say, well, do you want to unlock the lock?
Right.
So my recommendation is that you make a distinction for the user, that they know they're reading, and then when they come to want to make a change, you say, okay, I'm going to make a change. At that point, at least the user's in on the picture of, oh, this is something special.
Yes.
But that's a user interfacing thing and a user experience thing. That's not really my strong subject, so we say. But implementation of these things that user experience people dream up. Yes. I've been doing that for...
And the programmers that they write relational database, or they use a standard DBMS or MySQL and so forth, what do you think they should be cognizant about in this kind of setting? Because a lot of them, they just take that database for granted.
Well, I think it's useful when programmers at least understand the picture you see in front of you.
Yes.
That the process running here has some communication costs. The process is running here. You can't simply let the application server write onto the disk. You have to go through a DBMS to manage the different needs of different processes to make sure that the data is updated consistently. Yes. We've had DBMS systems, hierarchical systems, network systems, SQL systems, relational systems. Now we've gone on to NoSQL, which is going back to hierarchical and trying again, going back to network and trying again. And now you'll find that NoSQL stands for not just SQL. So we've got relational, we've got hierarchical, we've got network as techniques, but all of them involve a DBMS, a database management system. So that will always be there. So it's useful to understand what that thing is and what it does and what it prevents and what it's for. So if people don't understand this technology and they just use, shall we say, hibernate, and they say, persist this data, I don't want to know about the database systems. Just persist this for me. Then
Yeah.
they've lost out on a whole bunch of knowledge to do with performance. So for
Precisely.
small systems, yeah, great. But for larger systems, if you haven't understood this corner of the industry, then you're not going to be able to write applications which perform well, especially when you move on to projects which involve more and more and more data, and especially if you get involved in big data.
Correct. So truly understood that the core function of the database becomes the centrifuge and the heart of read, write, access, edit, modify, all of this record keeping that we have to do. And then through topology, through software configuration and memory management, like you explained, like CPU management and so forth, both from the front end to the back end, because now you're building a client-server relationship, and enables us to approach the locking initiatives based on an intelligent strategy. Is that the fifth resource that you were really trying to stress, that locking becomes the
What
element?
I'm trying to say is if you're looking at solving performance problems, you
Right.
have to understand where the bottleneck is.
Yeah.
And you do that by looking at monitoring systems.
Yes.
So I'm going to go back to the beginning of the presentation. Just run through it again.
Yeah.
Is the problem on the PC?
Yep.
Is the problem with the disks?
Yes.
Is the problem with the DBMS?
Yes.
Is the problem with the application server or application servers? Where is the performance bottleneck? Where are things being held up? If you can't answer that question, you can't even start working.
Correct.
Now, if I skip down through a little further, and go through to the CPU power thing again, and we want to understand, are we locked on CPU? Well, very unlikely. You know, if you're 100% CPU bound, it's you're streaming video, for example. That's quite a reasonable reason to be in a situation we're in now, where there's lots of feeds, there's uploads and downloads. They all have to be dealt with and processed and turned into pixels. Yeah, that's very costly stuff. That's CPU bound. But not many people work in a CPU bound area because the CPUs are so damn quick and so cheap. So it's very unlikely you're going to be CPU bound.
Understood.
And if you look at memory, let's go through these slides again. Sorry about this, a little bit slow.
No problem.
With index it for myself. If you look at memory, it's either going to be a problem with the PC of the user. The only thing you can do about that is not write JavaScript.
Mm-hmm.
Then you've got memory problems in your application server. Yeah, if you haven't got enough memory in an application server, and it's swapping and paging, well, you can spot that a mile off. Yep. But it's far more important if you haven't got enough memory in your database systems.
Yes.
Because then you're unable to cache data, and it doesn't show as a problem. Because if it's a problem in the application server, you'll be doing things called paging and swapping.
Mm-hmm.
Yeah, paging is where you're asking for some information which you thought was in memory, and it's actually held on the disk. It's being pulled in. Swapping is where you're swapping things out, swapping whole processes out.
Yes,
so
correct.
You don't want either of those things going on in the application servers. However, memory in a DBMS system, you can have a lot of memory there, so you're not getting paging and swapping, but the DBMS also knows how much memory there is and uses as much as possible to avoid having to do these very costly transfers from disk to memory. So when you're reading stuff, if it finds it in memory, the answer's straight there. If it's not there, it's going to have to move ahead, move the head of the disk, get to the right place, read the information, feed it back to the DBMS before it passes it back. So that can be the difference between a microsecond and, shall we say, 10 seconds if it's a large amount of data. So
can I ask something?
Peter.
Yes. Nowadays, you see more that more important than the programming language. One of the main challenges to developing for the clouds is the understanding how application servers dependencies are handled. Application servers dependency include this database, message server, or other servers deployed in a distributed environment. So you see, the nowadays programmers does not know what's happening behind the surface, and that means on the database they don't bother about that. Traditionally, this has been actually handled by mapping servers references to the physical IP. during the deployment process. So this could be also a problem. How do you see that, Graham?
Well, if you look at the complexities of providing services in the cloud, what the cloud providers have done is they provided libraries and mechanisms to make it easy to write programs for that environment. But all of them depend on an abstraction. Levels of abstraction where you're moving away from your understanding of disk and memory and CPU, and you're moving to understanding of, oh, that cloud provider does this cloud provider does that, and this is how much money it costs. So let's look at why people move to the cloud. Typically, you don't want to have your own computers. You don't want to own as many computers as you could have if you had something in the cloud. You don't want to own them. You don't want to have them in a building. You don't want to have people operating them. You don't want to have people doing backups. You want to just outsource all of that away so you don't have to do that work, don't have to consider it. But you are then moving away from efficiency, if you like. So efficiency, I'll give you an example. It's not a cloud example, but it's an example in general. I was working for a lottery, and the lottery needed to generate some bingo cards for all the people who are members of the lottery, of this recurring lottery. And they had a system made by one of the suppliers, and after 24 hours, it still said loading. And my attitude at that point was, well, what exactly are they loading? Because why would you load something? Surely you just want to take two files and merge the two files together to do this particular operation. You shouldn't be loading the file to do the merge. You just need to merge as you go. And I couldn't communicate this idea to the programmers. They didn't follow it. So I had to write it myself. And rather than running 24 hours without actually achieving the result, the whole thing was finished in 5.5 minutes. And that's because if you have an understanding of the resources you're using, in this particular example, I had two files, right? I didn't use a database, just had two files. I wrote a program in C which said read a record from here, read a record from there. If they're the same, do this. If they're different, do that. It was a very simple, very old-fashioned program called balance line. And it didn't use a huge amount of memory. It didn't use a huge amount of CPU. It just read one record from a disk and another record from the other disk, and then processed it and wrote it to another disk. So I optimized it to have 3 disks. And it turned out on the computer I was on, the 3 disks ended up on 1 disk. So that optimization didn't work on my computer, but it did work on others. And it was done in 5 minutes. So if you don't have an understanding of the nature of the machine you're using to solve the problem that the business has given you. So for example, if someone said, do that in the cloud, issue 50 million bingo cards in the cloud. Well, I would just say, well, why would I want to do that in the cloud if I can do it on a local computer where I have control over the disks, where I have control over where the program runs, how much memory it uses? So cloud can be a distraction sometimes. It's wonderful technology, and it's great for web applications, etc., but it's certainly not usable for everything. And it abstracts you from these rather simple concepts I've been putting out today about the CPU, memory, process communication, and disks. And it takes you into this world where you don't actually get to observe those things. So it's very difficult then to see what can I do to make this faster, other than buying more compute time. Does that make sense, Peter?
Yep, absolutely. I think at the view of the cloud development, you are not guaranteed what kind of IP addresses the application will be using, or it will look up services or data. So that the developer needs to have a solid understanding of using services in a very smart way.
I absolutely agree, but I have no idea about that stuff. And my experience is, if you've learned it, 2 years later, your knowledge is out of date and you don't understand anything anymore, and you have to learn it again. And 2 years later, it's all changed again. Example, Docker, it wasn't around or popular some time ago, and it won't be around or popular in a couple of years' time. There'll be other things. So the things you learn sort of disappear between under your feet. If you learn this stuff, the topography of multiprocessor systems, this stuff on the screen here right now, if you learn that basic model, you can do an awful lot. Because then there's only these 5 resources: CPU, memory, messaging, input, output, and locking.
Yep.
That's all there is. And basically locking, you can see if a machine is CPU bound, right? There are ways of seeing how much memory is being used, and if there's problems to do with memory, like paging and swapping. With messaging, you can also monitor the number of messages going to and fro. You can monitor the latency. You monitor the transfer speeds. You can see if that's your bottleneck. With input and output, you could just put your ear against the computer's housing and say, hey, click, 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 click. That sounds pretty good. That's not so good. You know, you can actually, these are tangible things. You can measure them. And if you've gone across your entire system looking to see, hey, what's the cause of my problem here? Let's go back. This bunch of things. If there's no CPU, memory, or disk or process communication issues here, or here, then you've got a locking problem. That means that even though all these things are working very well, instead of being able to process things in parallel, your system is doing things in a serial way. So if you imagine like a toll booth on a motorway, it's a 6-lane motorway, and the toll booth has 3 booths open. Well, you're going to have a bottleneck, right? And that's locking. It's because then you're not able to do things in parallel. And that's the most tricky problem that you have to solve, is that even though there's nothing clearly a bottleneck, everything seems to be running smoothly, but the system's still slow, then you have to find out which programs are blocking each other and how to make them work in parallel. So that's the same paradigm as multi-threading, or having multiple CPUs in a box, or multiple CPUs on a chip. Is, I don't know if you've seen this, I mean, sometimes you write a program, you say, I think this will be fast, and your CPU says 25% busy. And that's because you've got 4 CPUs and it's only using one of them.
Yeah.
So if you wanted to use all 4, you have to use this technique called multi-threading, which means you have to design your program so that the processes don't interfere with each other. And that's a much more complex aspect than any of the things I've touched until now. Writing multi-threaded solutions for big data problems, that's a very interesting field. That's when you're working out how to go and gather the information you want in parallel from all the database systems you've got, and then collate it without colliding.
Correct.
And
that's a whole subject by itself. Unfortunately, we are running out of time. I'd like to thank you, Graham. I'd like you to also to put your email address in here for us. So those of you who are interested in learning about really the fundamental thing that we all have been looking at it from, call it wireframe, if you will, before you put any skin on it, and understanding the methodologies of the CPU, memory, messaging, I/O, and locking, and integrating this into a foundation for your system management and growth, especially on the big data. That gives everyone an opportunity. So feel free to contact Graham at bolton.nl. He'll be able to send you information or answer, or he'll be available in some of the services through our continued education. Graham, thank you again for attending our session. Peter, thank you for being our host. Maddie, have a wonderful day, and we'll see you all next week.
Thank you.
Ciao for now.
Thank you, Graham. Maddie, cheers. Bye-bye.